Hi everyone, welcome to Data Platform Virtual Summit 2022. Today's session, building fault-tolerant applications with Azure Database for MySQL. My name is DSouza. I'm from the Azure MySQL engineering team. I previously supported Azure Database for MySQL, MariaDB, PostgreSQL, and on the Windows side, high availability storage and virtualization. And today, along with my colleague Rahul Saha, we'll take you through different sections of this session.
Thank you, Neil. I'm Rahul Saha, also part of Azure MySQL engineering team. I come from a background where I worked extensively in public cloud and open source database. I'm really excited for this summit and welcome everyone in Data Platform Virtual Summit 2022. Neil and I will take you through today's session in the next hour. So let's get started.
So in today's session, we'll be covering primarily the application resiliency concepts. In that, how we have implemented in Azure for the databases, mainly robustness and rebound. And we will be taking questions through the chat during the session. And with that, let's move on. So the resiliency concepts were framed by David Woods in his paper, 4 Concepts of Resiliency. And if we take a look at it, there are primarily robustness, rebound, which is something that can be implemented in the software, hardware, or the actual operations. And when it comes to extensibility and adaptability, they are more people focused. They're more related to the process and how we can deal with a situation and what resources to be engaged. And adaptability is how we can grow that into the changing environment and changing climate of disasters and so on. Now for robustness, basically to have mechanisms in the software and process to accommodate expected problems. These are something that we know that maybe the network will go down, maybe the storage will go down, or maybe something at the hardware level will go down, and how we can make sure that our systems can sustain that. There is a concept in high availability called as avoid anything that is a single point of failure. So always have another path or another piece of hardware that can be used whenever there is such a disaster. Rebound is, let's say there is a catastrophic disastrous event where everything goes down, and how we can come back from that to the best possible situation from where we were. And so when it comes to availability options, we have multiple different implementations in our Azure Database for MySQL. Here, going from the lowest RTO RPO to highest RTO RPO, and RTO RPO is basically the recovery time objective is RTO, which is maximum acceptable time before the application fully recovers after a disruptive event. Recovery point objective, that is RPO, is the maximum amount of recent data updates the application can tolerate losing when recovering after a disruptive event. And in our implementation, the RTO and RPO can vary depending on the implementation and the application. However, the cost and complexity always go high the lower the RTO and RPO is in general term. In backup and storage, we have like local redundant and geo-redundant. Wherein geo-redundant can recover from a more catastrophic event, but it will add to more cost. And similarly with high availability, with the same zone high availability and zone redundant high availability, wherein the zone failure can be tolerated. Now, if there is a region level disaster, then we need to go for something called as a custom solution, which can be using data in replication or a combination with the geo-redundant backup, which will add to the cost and complexity. However, RTO and RPO can vary there, right, because of the complexity and the skills required and the time required. And how do we approach resiliency? So as a concept, right? So if we look at the availability requirements, so each application may have a different requirement, right? So some of them may require like above 99.99%, which is quite rare. It's maybe something very critical application or a something that cannot tolerate any downtime. However, most applications should be good with availability of below 99.99%. So if we talk about so availability of a solution, it may have different pieces, different aspects of it. Could be high availability at the storage level, network level, or at the compute level, and combination of all this make up the system. So it's not a single thing, but availability can be different across different aspects of the solution. Don't think of robustness as a single big problem, because it never is a single big problem. There are different components, different parts to it, and we can have different workable solutions that provide us the highest availability. In terms of availability as well as the response time, latency, or in case of disasters, how durable the data can be in our storage subsystem or could be in the backup layers. And next we look at what difference does an extra 9 make in the availability SLA that we define, right? So if we look at 99.9%, downtime per year is almost close to a working day, like working business day, 8 to 9 hours, right? In a month it is 43 minutes. Now if we just add another 9, that comes down to less than an hour a year and less than 5 minutes a month. So that shows the impact of just having an additional 9. And we also have 99.95 because of the application requirements. Could be that they need something somewhere in between. And the next section will continue on to robustness, which will be taken by Rahul.
Thank you, Neil, again for the explanation about resiliency. We will further go ahead and talk about robustness. Robustness means that the system continue to function as intended. This is very important for any production system where system needs to continue irrespective of any challenge in hardware, network or storage. We will check on different deployment options in Azure Database for MySQL in the upcoming section. During the further discussion on resiliency, I'll be focusing on flexible server deployment, which is recommended deployment when you launch Azure Database for MySQL. Mission critical apps which needs high availability and fine-grained maintenance scheduling is one of the major use case for MySQL flexible server. Even though we have flexible server, we also have the other deployment for Azure DB for MySQL, which is single server. But we'll be focusing more on the MySQL flexible server on the upcoming section. Here's the architectural diagram for flexible server. Most of you have seen this earlier. I'll just try to refresh your memory. So flexible server runs on dedicated Linux VM which is zone aware. This means we can spin up MySQL to a preferred AZ, and when HA is set up, it can also be a cross zone. This is helpful when there is an outage. It can failover automatically to the other zone. Also, you could manually failover to the other zone. Zone awareness minimizes the latency as we have the option to co-locate the application and database to same zone. The second part is the storage. The storage is premium file storage which is separated from VM. It stores the data and logs into it. The premium file storage is replicated 3 times across the storage for better resiliency. So we can further opt in for same zone or zone redundant hot standby for high availability. In HA configuration, the data is synchronously replicated across the storage to support automatic failover and zero data loss. The failover typically takes 60 to 120 seconds. Can be expected to have a retry in the application with connection timeout more than 60 seconds. The database is automatically backed up and the backups are stored in locally redundant storage. But you can have an option to store backups on a zone redundant storage or a zero redundant storage to support data protection and disaster recovery scenarios. As the backups are zone and geo redundant, the backups can be restored to a different zone or region in case of an outage. You can deploy your application on VMs, VM Skillset, Azure Kubernetes Service, Azure App Service, and since the service runs on open source community version of MySQL, you do not need to refactor the application or need any additional drivers. It just works. So moving on to next section. Azure Database for MySQL Flexible Server allows configuring high availability with automatic failover. The high availability solution is designed to ensure that committed data is never lost due to failures and improve overall uptime for your application. When high availability is configured, Flexible Server automatically provision and manage a standby replica. When it comes to the billing part, you are generally billed for the provision, compute and storage for both the primary and secondary replica. As you can see here, there are two options when you configure HA in Azure Database for MySQL Flexible Server. They are Zone Redundant HA and Same Zone HA. When it is Zone Redundant HA, it is preferred to complete isolation and redundancy of infrastructure across multiple availability zones. And when it is Same Zone HA, is preferred for infrastructure redundancy with lower network latency, because the primary and standby server will be in the same availability zone. Let's move on to next topic. When you deploy Azure Database for MySQL Flexible Server with Zone Redundant HA, two servers will be created as you can see over the diagram. First is the primary server in one availability zone and the standby replica server with the same configuration as the primary server. That is also gets created whenever you create a HA. The configs of the replica server are quite similar to the primary server in terms of compute, storage and network configuration. The data and the log files are hosted in zone redundant storage, and these files are replicated to standby server via the storage level replication available with zone redundant storage. And in case there is a failover, and in that scenario it can automatically failover to the other VM or the other replica server. And whenever there is a failover, during that time the standby replica is activated and the binary log files of the primary server continue to apply to the standby server to bring it online to the last committed transaction on the primary. And lastly, the logs in the zone redundant storage are accessible even when the primary server is unavailable. The availability helps to ensure there is no loss of data. After the standby replica is activated and binary logs are applied, the current standby replica server takes the role of the primary server, and the entire process, after this process, the DNS is updated so that client connections are directed to the new primary when the client reconnects. This failover phenomena is fully transparent from the client application and does not require any action from a customer side or a user side. The HA solution then brings back the old primary server when possible and places it as a standby. Moving on. So here you can see the servers are deployed in same zone HA. So it is quite similar to the other configuration. Here also we have a primary server, standby replica with the same configuration as primary. And here the main goal is like it is infrastructure redundant. So it is separated. Both of the primary and the replica have separate virtual machines. The redundancy reduces failover time and network latency between the application and the database server because of co-location. The data and log files are hosted in locally redundant storage, and these files are replicated to standby server via the storage level replication available with locally redundant storage. And the failover mechanism is similar to what we have discussed earlier with zone redundant HA. It does the same thing whenever there is a failover, which is like the standby replica is activated and the binary logs are applied to the primary server, which is the same process which happens even though it is not the same zone HA. So it's very much important to understand when failover happens and how the failover happens in the background. So we have seen the architecture of flexible server for both zone redundant and same zone HA. I wanted to discuss more about the failover, which is important aspect of any production system. In general, there are two types of failover which can happen in Azure Database for MySQL Server. They are the forced failover, which is a planned downtime, or it's automatic failover, which is an unplanned downtime. Whenever there is a failure, the time needed for a standby replica to take over the role of primary depends on the binary log application on the standby. So we recommend that you use primary keys on all tables to reduce failover time. Failover times are typically between 60 to 120 seconds, but again it depends on the amount of load it's there in the database. So when we talk about forced failover, Azure Database for MySQL Flexible Server Forced Failover enables you to manually force a failover. This capability allows you to test the functionality with your application scenarios and helps make you ready for outages. When it is an automatic failover, we also consider it as an unplanned service downtime. It can be caused by software bugs or infrastructure faults like compute network or storage failures or any power outages that affect the availability of the database. If the database becomes unavailable, replication to the standby replica is severed and the standby replica is activated as the primary database. DNS is updated and the client reconnects to the database server and resume their operation. So this was an overview of a failover mechanism, how it happens in the Azure database. So here in this diagram you can see the single AZ deployment. So to summarize, Azure database of MySQL can be deployed either in single AZ or multi-AZ. When it is single AZ deployment, there is only a single server running, which is Azure Database for MySQL. Application connects to the database and it serves the request. This type of deployment is single point of failure, which means that in case there is some issue with the underlying hardware or any network issue, it would take good amount of time to bring back the service online. The MySQL service will come online, but the time taken to come online will be higher than the usual, which cannot be acceptable for the production workload. So here are some of the benefits or different scenarios of single AZ deployment. So while you have seen single AZ deployment, there are certain benefits of this type of consideration. For example, this type of deployment is least complex and very much cost effective. This is because the deployment is present only in single AZ. Also, we can consider it to be less complex because the traffic does not travel through multiple AZ. And because of this, it becomes very easy for any engineer to troubleshoot in case of any outage or any performance issue. Single AZ are most performant, but they are not robust enough as there is no server to failover in case of any issue in the primary server. Things can get even more difficult if there is an entire AZ failure. So generally, single AZ is not advised for production. It can be used while testing out the development work. Whenever it is a production environment, it should be always a multi-AZ deployment. So this diagram explains about multi-AZ scenario where the application might be in 3 different VMs in 3 different AZ connected to primary database in AZ1. And as this is multi-AZ deployment, the primary DB is also replicated to the secondary AZ, which is also known as a replica DB. This type of deployment is generally suggested in production, where the primary DB can fail over to replica DB in case there is any issue in primary DB. This type of deployment is also prone to AZ failure, and we'll see the benefits and consideration of multi-AZ deployment. Multi-AZ deployment is a robust deployment and most preferred deployment for any production workload. It can tolerate AZ failure for both database and application, and in case there are issues in primary database, the automation will automatically fail over to replica DB. Failover to replica DB or to the standby database can happen in between 60 to 120 seconds, but again, as I discussed earlier, this time can vary in accordance to the workload. Multi-AZ provides a great benefit, but there are different charges involved when we configure database across different AZ. Even though this is an extra involvement of cost, the robustness is not compromised. And lastly, there can be different response time depending on the AZ from which the backend is calling the database. This adds more complexity and performance overhead. Connection pooling is one of the important part of database, which improves the performance of any application. It is especially important for application which creates lots of short-lived connections. So this answers the first question, where you know now where exactly connection pooling should be implemented. Coming to the second question, there are various ways to implement the connection pooling. You can either create on the server side, or you could do connection pooling on the client side, or even you could do both. For MySQL, you can configure the connection pooling like proxy SQL on the application side. As you know, proxy SQL is a very well-known connection pool and load balancer for MySQL. On the client side, it is kind of library thing. It could be a sidecar in case of Kubernetes, or it can be configured in a dedicated VM. Client side is the most preferred connection pools. Let us look into best practices of connection pooling in the next section. We configure connection pooling, but it is very important to follow few of the best practices. As we discussed earlier, proxy SQL is set up at the client side for MySQL. It is very important to size the VM properly so that it improves performance on memory, socket and CPU cycles. Apart from that, there should be continuous monitor of open connection, idle connections and response time so that we can understand and improve the configuration of proxy SQL. Moving on. What is proxy SQL? Proxy SQL is the most used connection pooler in MySQL. It is an application via proxy which can do rewriting, sharding rules, and it is a lot more flexible. The most important feature of proxy SQL are that you can send read-only traffic to replicas using proxy SQL. You can rewrite the rows, you can check the source of the connection, and there are lots of other features on it. These are more about application layer proxy than purely connection pooler. So it gives lots of flexibility in the case, especially rewrite and sharding. The most preferred feature used out of so many users is that you can split your workload between primary database and multiple replicas. You can create scale set inside proxy SQL as well, like scaling rules are like you can create bunch of select statements, route them to one of the available read replicas in the particular topology. Similarly, if there are DMLs and DDL, you can route them to primary DB. Similarly, it also allows for certain rewriting policies so that you can mask some of the column level information. So this would make the application be different to what it is present under the database. These are some of the capabilities, but more you customize proxy SQL can be more effective for you. Lastly, proxy SQL is not deployed with pass offering. You deploy it in Kubernetes as a pod, which can give some high availability to it. You can also deploy it on application server, especially in cluster or in VM, which will give high availability feature. So moving on, we'll be looking the internals of proxy SQL. Proxy SQL internals have some important modules, which is user authentication modules, host group manager, which will be sitting between the servers and send the traffic internally, the connection pooler itself, why you are talking about it, and lastly, it got its own monitoring module. Monitoring is one of the critical aspects why many users leverage proxy SQL, like the replication lag. And the replication lag can be sometimes 0 seconds, 1 seconds, or few seconds. And sometimes it can be several minutes, because as we know, replication is synchronous in nature. As it is having monitoring inbuilt feature, it can be used to redirect the read-only queries to the replica, which is having the minimum replica lag. In those cases, proxy SQL is much more efficient than writing some custom code in application. When we implement everything in proxy SQL, it takes away the load from application side and takes care naturally. So these are some of the important features about proxy SQL and its internal mechanism. So next, we'll be checking more of the application side, how to handle the failures in the application. So when we are designing a fault tolerant application, it is very much important to handle the failures in application, which we are going to discuss in this section. Let us consider a transient error, also known as transient fault, is an error that will resolve itself. Most typically, this error manifests a connection to the database server being dropped. Also, the new connection to a server cannot be opened. So this transient error can occur, for example, when hardware or network failure happens. Another reason could be a new version of past service that is being rolled out, and most of these events are automatically mitigated by the system in less than 60 seconds. So as a best practice for designing and developing application in the cloud is to expect transient error, assuming they can happen in any component in any time, and to have the appropriate logic in place to handle the situation. Transient error should be handled using a retry logic, which we'll be discussing further. And few of the issues which are very common and you might have faced while designing and talking to application team are: an error occurs when you try to open a connection, or a ideal connection is dropped on the server side, or when you try to issue a command which cannot be executed, or an active connection that currently is executing a command is dropped. These are probable issues which can happen in the application side. So the general advice is to have the retry logic and have it can have the transaction retry, then setting up the timeouts in application, and also there can be a, if suddenly there is a surge in connection, there can be a back off of connection, or you can say exponential back off. So these are some good way we can implement in the application so that the failures can be handled. Failures are common, but it's very important for us to understand how it can be handled from the application side. Database scaling is also an important aspect while you design an application. It can scale the database resource to handle the demand. It scales up and down, and it is fully managed. So there are different type of SKU which is designed as per the workload. For example, as you can see, there are burstable, general purpose, and business critical. So while we talk about burstable, it is best for the workload that does not need full CPU all the time. And when it comes to general purpose, it is best for the workload which needs balanced compute and memory, and it is suitable for all the production business workload. And lastly, as you can see, the business critical, it basically suits for very high performance DB workload. So the business critical database instance which are built or which you can select, they have very high compute and high memory. So it is designed that way that it can handle the very high workload and the performance is not affected. So at any point of time, there can be a need to scale up this database instance, and if the workload decrease, we can scale down the database instance. So it is a part of the fault tolerant, or it is a part of the application design which should be kept in mind while you are talking more about fault tolerant applications and database. There are some higher SKUs which are in preview. You will see more SKU being generally available in coming days. Moving forward, we will see the different type of database scaling. So here, as you can see, database scaling, one of the very important part is the read replica. So as I said earlier, database scaling is very important for any production workload. Replicas can take on the load for the read queries, and primary database can offload some of the hits. Azure Database for MySQL supports read replica out of the box. In Azure Database for MySQL, you can create the read replica which is fully managed, and it can go up to 10 read replicas. When you would like to scale out the read workload from primary to read replica, creating replica is the best option. Some of the important use case is when you want to use the database for BI and reporting purpose, for any analytical purpose, or you have a IoT database where you write one to read many times from those workload. So these are some of the important things we always need to keep in mind while we design any type of application. Next, we'll be looking the caching. Caching is a common technique that aims to improve the performance and scalability of a system. As you can see, there are different tiers in caching like database layer, Azure Redis cache, and the application layer. Azure Redis cache sits between the application and database. Each of these tiers can work and be maintained independently, and in most cases be in different hosts also. Therefore, every time the application queries for data, the speed is limited by network performance, so that is one of the issue. But data retrieval time plays a key role in user experience and is a critical requirement in almost all commercial applications. Cache is a high-speed data storage layer which stores a subset of data, typically transient in nature. So the future requests for the data are served faster, that is possible by accessing the data's primary storage location. Caching allows you to efficiently reuse previously retrieved computed data. Some of the things which can improve when you're using cache are, it will be improving the application performance, it will reduce the load on the backend database, then the predictive performance for frequently accessed data, and then it is very much useful for eliminating any database hotspot. And lastly, it increases throughput as application hit cache for reading data. So next we will be looking some of the caching consideration which can be very important at times. As you have seen, caching is one of the important consideration. When the caching is done correctly, there is an exponential performance improvement. As you know, there are two types of caching, that is shared caching and local cache. And shared cache should be used instead of local cache, just because shared cache can serve as a common source that can be accessed by multiple processes and machine, which is not possible by local cache. I would suggest using cache where you need to store, session store, or very frequent access data. These things can improve the performance greatly, but the challenge comes to users when they do not know what data should be cached. So it is very important to understand the application and cache and the data accordingly. And as a best practice, use a managed cache, but do not use a cache as a database. It can lead to catastrophes. So moving on, we'll see the different caching strategies which are present. So there are different ways to set up caching layers adjacent or in front of the backend database, or choosing right caching strategy. So these are very much critical for any performance improvement of an application. So different strategies caters to different application natures, whether they are write heavy or write heavy in nature, what the data consistency should look like, and so on. So we'll discuss few of the important caching strategy, and to start with, we'll start with something called cache aside. So this is one of the very commonly used caching approach. The cache sits on the side and the application directly talks to both the cache and the database. So whereas if you consider read through cache, here read through cache sits in line with the database, which means when there is a cache miss, it loads missing data from the database, populate to cache and return it to the application. And there are other type of cache also, which is like write through cache. In this write strategy, data is first written to the cache and then to the database, which means that cache sits in line with the database and writes always go through the cache to the main database. So there can be different strategy which are preferred for different application. So there are other cache like write around cache. Here data is written directly to the database, and only the data that is read makes it the way into the cache. And last one, as you can see, which is write behind cache. So here the application writes data to the cache, which acknowledge immediately, and after some delay it writes the data back to the database. So all these are different type of caching strategies. In practical world, it is very much important to carefully evaluate your goals, understand the data access, read or write pattern, and choose the best strategy or a combination. So what happens if you don't choose it correctly? it is very much important that you choose it correctly, because if you do not select it correctly, it does not match your pattern, you may introduce additional latency, or at the very least not see the full benefit. So for an example, let us consider if you choose write through and read through when you actually should be using write around and read through, so that written data is accessed less frequently. So in that case, you will see you will have useless junk in your cache. So if the cache is big enough, it may be fine, but in the real world high throughput system, the memory is never big enough and server costs are really a concern. So the right strategy really matters in these scenarios. So moving on, we'll see the another important aspect of database is the maintenance. So maintenance is an important aspect in any type of database, as the bugs needs to be resolved, OS needs to be updated from time to time. So Azure Database for MySQL also have maintenance feature, which where there will be a patch applied in your preferred time in flexible server, and this time period is 1 hour. So during this 1 hour, your maintenance would start, and when this maintenance start, you can expect a downtime of 60 seconds when it is multi-age environment. And the best part is that the next maintenance would happen only after 30 days. So you have plenty of time to replan your application changes, and you do not worry about any maintenance happening sometime soon. Also, as it should not be a surprise for you, Azure sends the notification 5 days in advance, so that you can plan your entire journey, what happens when when this maintenance would start. And as you know, we also update minor MySQL version as a part of scheduled maintenance too. As you have seen so many things in all these slides, hope you have learned something good today, and there it would be really useful for you. The last section is rebound. For that, I will hand it over to Neil to take it forward. Here you go, Neil.
Thank you, Rahul. Now to come to rebound, how we implement in Azure. Rebound basically means if after traumatic event or a disaster, how the system can be returned to the previous function, or how well we recover, like how much loss or what would be the minimal loss we can sustain when we recover. We'll discuss about this concept. So let's start. So how it is implemented is primarily using a backup restore of the database. So the Azure Database for MySQL comes with automatic built-in backup with default retention of 7 days, which you can configure to from day 1 day to 35 days. It can be changed at any time, and we take snapshot based backups on a daily basis, and binlog archival backup every 5 minutes, so that it can be restored to point in time using a combination of the snapshot backup and the log backup. And the other option is geographically redundant backup, which will also make a copy of the backup to the paired region of the region where the MySQL server exists, and from the copy in that paired region, in case of a disaster in the primary region, it can be restored to any region. Moving on. So let's go in depth into the PITR, or the point in time restore. So a PITR, when you do a restoration, the server is restored in the same subscription, resource group, and the same region with the same database version. However, if you have configured with the public network or a private networking and you wish to switch that, at this point in time, you can do that when you're doing a restore from PITR. And you have multiple options to restore: latest restore point, custom time, and fastest restore time. Latest restore time is the latest backup that is available, which is the combination of the snapshot and the log backup. Custom time is you can choose any point in time within the retention period, and you can restore to that, which will again use the combination of the snapshot backup as well as the log backup. Fastest restore point would let you restore to a point in time which is the snapshot backup, because the restore performance is faster when you restore to a snapshot backup, since log backup need not be replayed. However, when you do a PITR, you must choose a different server name. Same server name cannot be chosen, and however, you can still choose a availability zone other than the where the primary server existed. Snapshot restoration is done at the storage layer, and further, if it is a custom time or the latest, the logs are restored and replayed, which can take some time, and from the last restore. So snapshot is restored at the storage layer, and further, if you have chosen a latest or a custom time, logs are restored and replayed. This could take a while depending on how much logs need to be replayed from the point in time of the snapshot backup to the time that you have chosen. Moving on. So disaster recovery. So if there is a failure at the region level, what are the options available for us to prepare for that and restore from it? One option is geo-redundant backup restore, which can be configured when you create the server, and DR can be across the geo-paired region, which can be low-cost DR. You get a higher RTO and RPO, and you can create DR instance on demand. And when you do the restoration, it can be the backup is copied to the paired region, and the restoration can happen to any of the region from there. Okay, the other option is data in replication based DR, which is a customer managed solution, and you can configure replication to the same region or another region. Basically, it need not be a paired region, it can be any region, and it provides a lower RTO and RPO and uses the MySQL native replication restrictions they may apply. And moving on, let's talk about geo-redundant backup in a bit detail. So we get 16 nines durability of objects. Backup storage used for geo-redundant is twice that of a locally redundant server. It's because when we take a backup in the locally redundant storage, the same copy is maintained in the paired region, which will take up that additional storage. Geo-redundancy can be enabled for locally redundant backup storage after the server is created as well. This is a capability in a flexible server. Currently, only create time experience for HA enabled servers. So which means that the switch from geo to local cannot be is not possible with the servers with high availability enabled. And backup of a geo paired region and delay could be up to 1 hour RPO. Basically, if a disaster strikes, the amount of lag that you may have after you restore could be up to 1 hour. Geo restore on demand restore from the latest geo backup at the paired region. So geo restore cannot be a point in time where you can choose a particular time. It will always be the latest available backup, and RPO would be up to 1 hour for potential data loss with the geo restore. So let's move to the next section. So let's consider a scenario of a database server located in the East-US2 in availability zone 1. And we may have an application either hosted in Azure VM, AKS cluster, or a Azure App Service. It can be any of that which is connecting to the MySQL server using our premium storage, where we maintain the data and the bin logs. And you can also see the backup storage which is maintained here for that region. Now let's assume a disaster strikes the availability zone 1, and we need to restore to the different region. Let's say the region is Central US in availability zone 2 in Central US. And since the backup storage copy is maintained in a paired region, though the East-US2 is not available, we can use that and create the server in Central US with the latest backup available. And the application can be rerouted to connect to the new database server, which is restored from the latest backup. So let's consider a scenario of a multi-region deployment, where the application could be a distributed application, wherein it may be stateless or stateful, where it may have users connecting from a particular region reach the application closest to that region, and or we can have like an active passive configuration where region 1 is active, region 2 is passive. So what happens in this case is we may have a traffic manager which can check the for the application. So in this case we are taking an example of the application implemented in AKS. However, the same can be considered if you have deployed similar infrastructure in a virtual machine, and if using Azure App Service, a different high availability concepts may apply. So in this scenario, what happens if there is any disaster strikes the region 1 at the master, wherein we have a read replica in the region 1 as well as a second replica in the region 2, which is basically passive and standby at this moment. And when the disaster strikes, the replica in the paired region can be made into a primary, and the application traffic can be routed to the passive application side, which can continue using the database on the region 2, and the application can continue working. The replication between the two regions will need to be the native replication using the logical replication in MySQL. Since currently it doesn't, the platform doesn't have a capability, we can still set it up using the native logical replication of MySQL. Multi-region deployments are most complex and expensive deployments. We are currently unable to have active setup using relational databases. We can do active read write and active read, however generally it is not recommended, but best approach is to have an active read write in primary and the passive or standby in the second region, and use a API manager proxy in the middle which can route the reads and writes. The caveats could be consistency in certain use cases. The more components the customer adds to the application, the more complex the design would be. It can be better used to recover from region failures. Clusters can be left scaled down depending on RTO. Replica can be promoted to master when needed, and you can also plan for failback. That is, once the region is back, can recreate the server from the latest backup available and configure the logical replication, native MySQL logical replication from the new primary to the secondary server that you're going to configure, and then you can plan the failback to come back to the primary region. We covered most of the questions through the chat, so we will cover some of the common themes here, and if you have any additional questions, we'll see how much time we have and we'll cover that accordingly. Now for some resources for you to go through later. Basically the official Azure Database for MySQL documentation, and we have some beginner series videos for Azure MySQL for beginners and MySQL Dev Essentials. You can get started free with an Azure free account and try out our Azure Database for MySQL flexible server and single server. If you have any questions, feedback, or follow-up, please reach us on Ask Azure DB for MySQL at service.microsoft.com. And for any updates for our product, you may subscribe to our Twitter channel, Azure DB for MySQL, and our LinkedIn page. And we have few of the other sessions delivered by the product group of MySQL on Azure. So you may go through that based on your interest. And here we reach the end of today's session. Thanks for your time and your interest. Please share your feedback for the session so that we can improve and do better. Hope you have a great rest of the Data Platform Virtual Summit.